So, for today's lecture, we are moving on to elementary particles. And so, a lot of the cutting edge physics, that's being done today in places like Brookhaven or CERN in Switzerland involves high energy collisions involving tiny particles. So in order to make those collisions happen, you need to accelerate the particles. And so, what's the process by which that's possible? So, high energy collisions can create new particles, and when I say new particles, particles that haven't been observed before. And theory has often led experiment as far as this goes. You think the Higgs boson, which was a fairly big discovery a couple of years ago, that was something that had been speculated on for a very long time, or speculated about for a very long time. But they were finally able to verify its existence only relatively recently. So the advantage of working with the higher momentum, meaning the faster the better as far as the collisions go, is that the particles will have a lower wavelength. Remember, wavelength is directly related to momentum. P is equal to h over lambda, or lambda is equal to h over p. So the bigger the momentum, the smaller the wavelength, and the smaller the wavelength, the more observable detail, the less uncertainty in your measurements. And that makes a difference. And so, the faster the better in that regard. And the accelerators we have today are a variation on the cyclotron. And if you remember physics 2, a particle under the influence of a magnetic field is going to move in a circular track, or at least a spiral track. And the speed is equal to q times b times r divided by the momentum, or rather, not the momentum, the mass. And the period, the amount of time it takes to complete one circle, is equal to 2 pi times r, the radius of curvature, divided by v. But from the formula here, the cyclotron equation, you can write the period as 2 pi m divided by q b. So the period ultimately doesn't depend on the radius or the velocity. It depends on the mass of the object, the charge of the object in question, and the magnetic field it's being influenced by. And the cyclotron frequency is just the inverse of the period. Remember, the frequency is the number of complete cycles per second. The time is the number of seconds per complete cycle. So the frequency is equal to QB divided by 2 pi m. Now, how do these accelerators work? So typically, with accelerators, you have, instead of a complete perfect circle, you have two D-shaped cavities called the Ds, with a narrow gap between them. And so you have an alternating potential difference that accelerates the particles as it goes around. Um, so you have a potential difference that's accelerating it to a point, then it crosses that point, and then the potential shifts, so then it gets accelerated again. And, so there's not a constant potential, but rather an alternating potential. So alternating positive, negative, positive, negative. But if you set it up the right way, the alternating positive, negative can keep the acceleration going. And the faster you get it to go, the greater the radius of curvature. And eventually what you want to happen is that the particle reaches the outer edge of the cyclotron where the target is and strikes it. And so that's an example of a particle with a stationary target. And the frequency, if the speeds involved are not relativistic, then the cyclotron frequency doesn't change. However, going back to the equation, um, so if you write, let's set it up like this. That would probably be the easiest way to do that. Um, the basic cyclotron equation is that the radius of curvature is equal to mv times qb. And from that, you get the ratio v over r is a constant, assuming the mass is constant, the charge is constant, and the magnetic field is constant. But if the speeds are relativistic, meaning the object is moving at a speed greater than the 1/10 the speed of light, that old factor gamma comes in. So non-relativistically, the numerator is the momentum, and in relativistic speeds, the numerator is the momentum as well, but now it's gamma mv divided by qb. And that's an important distinction because now the ratio v over r is no longer constant. And so with the cyclosynchrotron, you have to adjust the frequency. You can't have one frequency, one steady frequency. That won't work. And excuse me. And so you have what's called the synchrocyclotron. I think I said cyclosynchrotron. It was the wrong way. Synchrocyclotrons. And so it was, you have synchrotrons, so you have to adjust either the frequency or adjust the magnetic field if the speeds become relativistic. Again, the cyclotron frequency is no longer constant if the speeds are relativistic. You have that multiplying factor gamma that you need to take into consideration. Charged particles will radiate energy as they accelerate. So that's called synchrotron radiation. And another example of accelerator, so those are all circular accelerators, but it's possible to accelerate using a linear accelerator, where again, the electrons are accelerated through alternating voltages. And so, you have an electron, if it's basically you set up an alternating current so that it's positive, negative, and at different stages in the on the path, and that as the electron gets accelerated through a positive potential difference, and so it's positive, and then when it enters the negative region, the frequencies shift. So now it's traveling through a positive region again, and it continues to accelerate. So that's what a linear accelerator is. And then we have, instead of hitting a stationary target, we can have moving targets. So we have colliding beams. And so, we get the objects to move in both directions very quickly relative to a stationary observer. They'll be moving even faster than that relative to each other. But again, you do need to take relativistic effects into account, when analyzing this. And at really relativistic speeds, you can do a very simple approximation that E, the energy of the particle, is equal to P, the momentum of the particle, multiplied by C. Remember, the relativistic energy equation is given by this, that E is equal to the square root of P squared C squared plus M squared C to the fourth. So the first term is basically a measure of kinetic energy. The second term is a measure of rest energy. And if the kinetic energy is quite a bit greater than the rest energy, then you can write this simply as E is equal to PC. So if this term can be safely neglected because it's much smaller than the P squared C squared term, then the kinetic energy can be simply expressed as P times C. Okay, so let's move on to an example. Calculate the wavelength of 28 giga electron volt electrons. So um, I will leave it to you to figure out that this is definitely relativistic. I mean, if you wanted to solve for 1/2 mv squared, you would get a number quite a bit above the speed of light. So we're definitely talking about relativistic speeds. So you can write the wavelength as being equal to um, so we have the energy is equal to P times C, and we can write that as hc over lambda. So it's just like a photon when you're going at those kinds of speeds. So lambda is equal to hc over E. So H is what it always is, 6.626 times 10 to the negative 34 joule seconds. C is 3.00 times 10 to the 8 meters per second. And then you have giga electron volts. So mega is 10 to the 6, giga is 10 to the 9. So that's 28 times 10 to the 9 electron volts. But don't forget that you have 1.60 times 10 to the negative 19 joules per electron volt. So let me grab a calculator real quick. Okay. Okay, so it has a wavelength of 4.4. We only have two significant figures, times 10 to the negative 17 meters. So that's a very low wavelength, which obviously corresponds to very high energy. But again, in a particle accelerator, you can get that kind of energy. So what strength of magnetic field is used in a cyclotron in which protons make 3.1 times 10 to the 7 revolutions per second? So the cyclotron equation, if you're talking about frequency, is F is equal to QB over 2 pi M. And so we want to solve for, we're asked for the magnetic field given the frequency, and given that it's a proton. So we know what Q is and we know what M is. So we have B is equal to, so we multiply both sides by the denominator here, 2 pi M F divided by Q. So that's 2 pi, and it's the mass of a proton. So that's 1.67 times 10 to the negative 27 kilograms. The frequency, we are told, is 3.1 times 10 to the 7 revolutions per second. And we can write that as hertz, complete cycles per second. So 2 pi mf divided by Q. And Q is just like for an electron, 1.60 times 10 to the negative 19 coulombs. And this will give you your answer in Tesla. And to two significant figures, it's 2.0 Tesla. And remember, a 2.0 Tesla magnetic field is a very, very strong one. It's about 100,000 times the magnetic field strength of the north-south component of the Earth's magnetic field. So it's a pretty strong magnetic field that's used in this case. Now we're going to talk about some of the particles beyond protons, neutrons, and electrons that have been found in these collisions. But again, sometimes theory leads the collisions. So, excuse me. So a Japanese scientist, Hideki Yukawa, predicted the existence of a particle called the meson in 1935 that would regulate the strong nuclear force, and which led to Richard Feynman developing the theory of quantum electrodynamics, was the idea that all the forces are regulated by an exchange of particles, and that for the electromagnetic force, for example, photons are the regulators of the force, that objects exert electrical and magnetic forces on each other by exchanging photons. So the first type of meson we're going to talk about is the pi meson, or the pion. And so we have three: the pi plus, the pi negative, and the pi zero, the pi neutral. So the pi plus meson has a charge of positive E, and again, E is 1.60 times 10 to the negative 19 coulombs. The pi negative meson has a charge of negative E, and the pi zero meson has a charge of 0. The first two are each other's antiparticles. So one is matter, one is antimatter. They have an identical rest energy. The pi zero meson, or the neutral one, has a slightly lower rest energy, 135.0 megavolts per c squared, as that's the rest mass. So the rest energy is 135.0 mega electron volts. And so quantum electrodynamics led into what's called quantum chromodynamics, which says that protons and neutrons and other particles involved with the strong nuclear force are made up by something called quarks, and that the particle that regulates these interactions is called a gluon. And basically, the gluon is what holds the nucleus together. And so, the gluon basically means glue. And so, for the strong nuclear force, it's the gluons. The electromagnetic force is about 1/100th the strength of the strong nuclear force for two protons in an atomic nucleus. And again, the photons regulate the electromagnetic forces. The weak nuclear force is about 1/millionth the strength of the strong nuclear force. And the particles that regulate weak interactions are the W positive and negative, and the neutrally charged Z particles. So W positive, W negative, and Z zero. And then we get to the gravitational force, which is utterly negligible at the nuclear scale, 10 to the negative 38 the strength of the strong nuclear force. It's been postulated that a graviton regulates the gravitational force, that there is some sort of particle that regulates the gravitational force. It has not been found yet. Uh, so theory is definitely leading experiment in that regard. There to be a very significant discovery if a graviton is detected, but we don't have the means of doing that yet. So now we're going to talk a little bit more about antiparticles. So every particle basically has an equivalent antiparticle, which is basically, so it's exactly the same thing with an opposite electrical charge. So the positron, for example, is an electron with a positive charge, as the same mass as the electron. All the other properties other than the sign of its charge are identical to the electron, but it has the opposite charge and is considered the antiparticle to the electron. Dirac required the existence of positrons in his solutions for the relativistic wave equation in 1928. So Dirac, he expanded the Schrodinger equation to include objects moving at relativistic speeds. And so that's where the spin quantum number comes from, the solutions to Dirac's equation. And but one of the consequences of Dirac's math was that it allowed for the existence of positrons, or opposite, basically anti-electrons. The positron was first detected in 1932. So again, theory-led experiment by a few years. But the antiproton, so just like a proton except negatively charged, wasn't observed until 1955. So, and I've already said it a few times, and what you see with particle physics a lot is the theory leads experiment. The theory is well ahead of our experimental, our ability to experimentally verify things. And that was true in 1928, and if anything, it's more true now, nearly a century later. So if a particle and its antiparticle collide with each other, they will annihilate each other. The masses will completely be converted into energy and produce gamma rays. So a matter-antimatter collision will result in the release of quite a bit of energy. Basically, all that mass instantaneously becomes energy. And so you have high energy gamma rays, high energy photons. In particle interactions, the basic conservation laws as we know them at the macroscopic level still apply. Energy needs to be conserved. It's never created or destroyed. The momentum of the system, whatever it was before the collision, that's what it's going to be after the collision. And that's also true with angular momentum. And that's also true with electrical charge. That the charge never changes. Whatever charge you had before, you have after. One type of fundamental particle that we'll talk about, or general type of fundamental particle, are the baryons. And so these, that's another way of saying nucleons and antinucleons. So nucleons are protons and neutrons. Baryons are all, include antiprotons and antinucleons. So baryons are nucleons plus their antiparticles. So protons, neutrons, antiprotons, and antineutrons. Nucleons have a baryon number of +1. Antinucleons have a baryon number of -1. So an antiproton has a baryon number of -1. An antineutron. Neutrons do have antiparticles. The sign doesn't change, but they're still antimatter, and an antineutron and a regular neutron will annihilate each other if they come in contact. Antinucleons have a baryon number of -1. The baryon number is conserved in interactions. So that's another uh, conservation law that you have, that the baryon number can't change. And so it's one of the ways of figuring out if a reaction is possible or if it's not possible. Is the baryon number conserved? Is energy conserved? Is momentum conserved? All these things. Um, so at the subatomic level, protons and neutrons are not fundamental particles. They are made up of quarks. So you can break those down, into combinations of quarks. And we'll talk more about quarks in a couple of minutes. But there are other particles, not just the electron, that also cannot be broken down any further, at least not to the best of anybody's knowledge. They cannot be broken up down any further. And the leptons are not made up of quarks. So an electron is an electron. It's not a quark, nor is it a combination of quarks. Another such particle is called the muon. It has the same charge as an electron does, negative V, negative 1.60 times 10 to the negative 19 coulombs. It is more massive than an electron. Its rest energy is 106 mega electron volts. The electron is about half a mega electron volt as far as rest energy goes. Electrons and muons also emit different neutrinos. So neutrinos can be emitted in certain reactions. The type of neutrino that gets emitted depends on what emitted it. So there is a difference between the neutrinos an electron emits and the neutrinos a muon emits. So electrons and electron neutrinos have an electron lepton number of +1, while positrons and positron neutrinos have an electron lepton number of -1. So again, and this is another example of a conserved quantity, the lepton numbers. And muons and muon lepton numbers, or muon neutrinos have a muon lepton number of +1, and their antiparticles have a muon lepton number of -1. And both those lepton numbers are conserved in interactions. So there are a few different numbers that, at least in total, can't change from before to after a collision. Now we're going to talk a little bit about the sun. Um, Theory has suggested that we should be seeing quite a bit more electron neutrinos than we actually are, coming from the sun. And but electron neutrinos can turn into other types of neutrinos through some sort of reaction or some sort of process. And as far as the mass of a neutrino, we've talked about this a little bit, about the different neutrinos, whether the mass is even different or the same. These are things we don't necessarily know. Scientists are confident that the mass of the neutrino is something greater than 0. At this point, the maximum number is about a millionth the mass of the electron. So it's very, very tiny. Tiny enough that we can't really, we don't have the precision to really get it at this point. Okay, so what I'm going to do is I'm going to set up a video for you so that you're talking about how neutrinos work. And so this is definitely more recent than the textbook. So there's quite a bit of information here. And again, this chapter and the last chapter kind of need updating on a regular basis. But this is talking about neutrinos and what we do and don't know about them. at least as recently as 2018. But I thought this was a pretty good um, explanation.
So let me introduce Andre Degouvier, who's from my own home department in physics and astronomy at Northwestern. And he's going to talk to you about neutrinos. Okay.
Hi, my name is Andre, and in 1 second, I'll talk about something completely different. So my job is to tell you something about particle physics. You might know that Fermilab is a particle physics lab, so it stands to reason that somebody should talk about that. Let me remind you of what particle physics is about. Particle physics is about understanding what everything is made of. We've been thinking about this for a very, 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 very long time, and it looks like a good type of question to be asking. And the best thing that we've been able to come up with is that everything is made out of these things that we call particles. So the jobs of particle physicists are to find out what are all of these particles, what do they do, and how they talk to one another. And the claim is that if you manage to do that, you explain absolutely everything. We haven't been able to do that, but we're having a lot of fun in the meantime. This is where we are today. You must have seen lots and lots of different tables of fundamental particles before. This is actually what they look like. So I do have to say that these are also for purchase. And if you don't have a particle at home, you can go to this website and you can buy one. And you can buy your favorite particle. So all of the fundamental particles are here. They're ordered in a very particular way. This good-looking picture actually has a lot of information in it, and I'm not going to talk about any of that. What I do want to concentrate on is in a subset of these particles, which are called neutrinos. So the neutrinos are these particles that live over here, and they're often referred to by the Greek letter nu. So if you see that written down somewhere, that's what the neutrinos are. So neutrinos are among the fundamental particles. They're kind of like the electron that everybody's very familiar with. They're kind of like the photon, and there's lots of them on me right now. And they're like things like the quarks and the gluons and all these weird particles that you've heard about in the past. Neutrinos are also the particles that we understand the least. And they're also the ones that have done something in the very recent past that we were not expecting them to do, which is why I'm going to be talking about them. What we've discovered about neutrinos is that they had particles that they had properties that we did not anticipate. So we found this out about 20 years ago. And my job in the next 5 minutes is to try to tell you what it is that we found out and why that's such a big deal. And the thing that we found out is that they have mass. And we found that out by a new phenomenon called neutrino oscillations. So I will try to explain what that means and how we found this out. And the first thing I need to tell you is that there are actually different types of neutrinos. And the different types are defined by how they are produced and how they're detected. And for the sake of this argument, I only need to talk about two types of neutrinos. There's a third one, which is kind of like those two as well. So for example, there are a bunch of neutrinos that are produced in the sun. The sun is a gigantic neutrino factory. And there's also a lot of neutrinos that are produced in radioactive decay processes. All of those neutrinos are called electron neutrinos. And we know how they're produced. We also know how to detect them. There's a different kind of neutrino, which is produced when, for example, cosmic rays hit the atmosphere. When cosmic rays hit the atmosphere, they produce a bunch of particles called pions, which are called by this letter pi that we're very familiar with. And when those pions decay, they also produce a kind of neutrino. And of course, we also do this in the laboratory, especially this laboratory in particular. We also produce a bunch of these pions. These pions decay, and we say that we produce a neutrino beam that way. And those are all muon neutrinos. So these are different types of particles that are produced and detected in different ways. If you don't believe me that they're different particles, we're very, very sure that this happened because these people got the Nobel Prize in 1988 for proving that this is actually true. The electron neutrino and the muon neutrino are different particles. This is Leon Lederman that many of you may have seen before. He was a Fermilab director for a long time, and he passed away earlier this year. So their job was to show that the muon neutrino and the electron neutrino are different particles. So something funny happened, however, is that we found out that it's possible to produce a particular kind of neutrino. But if you wait long enough, and you detect it, it can behave as a different kind of neutrino. This is something that happened 20 years ago, and we're still working on this to figure out what it means. But we're very, very sure this happens. There's a long list of different types of experiments that have seen this phenomenon, and we're very, very sure that this happens. And what's really important about this is that this proves, or this only works if the neutrinos have mass, which is something that we didn't know before. So the way this works, if my volunteers will rush in because they forgot, is I want to try to explain how this works very quickly. And the way this works is because of quantum mechanics. So the one thing you want to remember, which everybody has heard before, is that particles are waves. And because particles are waves, they have this wave-like behavior. And a good way of explaining a wave is to use a pendulum. So a particle that's propagating can be represented by a pendulum. So for example, if this pendulum is oscillating back and forth, then the particle that's associated to this pendulum is oscillating, is swinging back and forth. That's the picture. So this is one particle. This is another one. And it does the same thing. And the only thing that's important is that the properties of the particles are encoded on how this thing swings back and forth. So we're saying now that the neutrinos have mass, which means that the neutrinos are also things that look like this. So the question then becomes, I told you that there are two different kinds of neutrinos, the muon neutrinos and the electron neutrinos. So which one is which? And the answer turns out to be yes. Okay? What happens is that the electron neutrino and the muon neutrino are both of these things at the same time. So how do you tell them apart? You tell them apart by the way in which they oscillate, which has to do with the phase. So the idea is, the electron neutrino might be something that oscillates like this, okay? And the muon neutrino is something that oscillates like that. And you can ask, what happens if something in the middle is going on? And in this case, that object that's doing something weird is sort of a mixture of the two, and it has some probability of being a muon neutrino and some probability of being an electron neutrino. So that's the picture. And how do the oscillations happen? The oscillation happens because these different pendulums have slightly different frequencies. So let's say that I turn it on in the electron neutrino mode, and it looks like that. And then we wait. We let some time go by. And what I mean by wait in the particle physics lab lingo means I produce my neutrino here at Fermilab, and then I build a detector in Minnesota. And that's how much time you have to wait. But if you wait long enough, you see that they start to go out of phase. So what was born as a pure electron neutrino, all of a sudden now starts to have this component that's oscillating like that and not just oscillating like that. So if you keep following the pendulum, you see that it starts off like this. After some time, it'd be going back and forth like that. Then it'll be doing this again. So it's born as an electron neutrino, then it oscillates and it changes flavor from one to the other. Why is this very important? This is very important because our model, that pretty picture that I showed you before, makes a lot of predictions. It made one prediction, which is neutrino masses are 0, which means that our model is wrong. And what happens in physics is when your model is proven to be wrong, you get very, very happy. Because that means you're learning something. You predicted something and it turns out it's wrong. That's one thing that we learned. The other thing is that we also learned that neutrino masses are not 0, but they're very, very small. And let me try to just give you a sense of what that means by showing you this picture back again and by trying to map fundamental particles into animals. And I'll try to map them into mammals. The heaviest particle is a top quark, which was discovered here at Fermilab. If the top quark were a mammal, it would probably be a blue whale. The blue whale is the heaviest mammal that has ever existed. It's actually the heaviest animal that moves that has ever existed. So the top quark is a blue whale. The bottom quark, also discovered here at Fermilab, by the way, that's kind of like an elephant. It's a lot lighter than the top quark. And something like the muon, which is one of my favorite particles, that's kind of like a tiger. And of course, the electron is like a rabbit. So we've discovered that neutrino masses are not 0. So what do neutrinos look like? They look like this. These are not big flies. These are fruit flies. The heaviest neutrino is probably not heavier than a fruit fly in this scale. So we think neutrinos are very, very weird because they're not even mammals. Okay? Now, this is very important because we don't know how these masses happen. And we also think that they mean something very important. And because my time is up, I want to remind you that we're still doing a lot of neutrino experiments. Fermilab now has all of these different neutrino experiments going on for us to try to understand what's happening. Thank you.
Okay, getting back to our slide. So that's pretty fair analysis of the state of how things are with neutrinos right now. So how do we classify particles? Well, we have fundamental particles that are believed to have no internal structure. They're not made up of things. So quarks are a fundamental particle, and the leptons are fundamental particles. And then we have composite particles, made up of quarks. So the baryons, the nucleons, those are made up of quarks. And another type of fundamental particle that we're going to introduce are called gauge bosons. So these are fundamental particles that mediate interactions. So a photon is an example of a gauge boson. The gluons that we showed in the diagram, they mediate the strong interactions. So those are gauge bosons. And the W and Z particles mediate the weak interactions. And the leptons, again, are the fundamental particles that don't interact by the strong force, but by the weak force. And if they're charged, like an electron is, obviously, by the electromagnetic force as well. So the electron is a lepton, the muon is an electron. The tau particle is another type of lepton. And all their respective neutrinos are considered leptons as well. And again, the neutrinos are neutrally charged, so they wouldn't interact by the electromagnetic force, but definitely by the weak nuclear force. So hadrons are composite particles that do interact by the strong force. So the proton is an example of a baryon, which is an example of a hadron. So you have this hierarchy going on. And then you have the mesons, which are another type of hadron. These are particles that have short lifetimes, but they can be created in collisions. So the baryons, like protons and neutrons, for example, they're made up of 3 quarks. And mesons are made up of a quark and an antiquark. So a slight difference between the two. And so this is table 43.2 in the book. And so you have different examples of, the fundamental particles. You have the gauge bosons and the leptons. Then you have the hadrons, which are made up of quarks. And so you have the baryons, which are made up of 3 quarks. So again, the protons and the neutrons are examples of baryons, which are examples of hadrons. But there are other types of baryons. The lambda particle, the sigma particle, and they have different charges and different corresponding antiparticles. And so you have different particles involved with different rest energies in mega electron volts. And then you have the different numbers, the baryon numbers, the lepton numbers. And it's like you can see that, in the order of seconds, that most of the baryons are have very, very, very short lifetimes, and then they'll eventually decay. And so you have the different mesons, all of which have very, very, very short lifetimes. And so you have different different types of particles, and it's hard to get the hierarchy down pat initially. But again, protons and neutrons are examples of baryons, which are examples of hadrons. So And again, a baryon is any type of nucleon or its antiparticle. A hadron is anything that's made up of quarks, which includes baryons, but it includes other things as well. So now we're going to go to an example about how much energy is released when a lambda zero particle decays to a neutron and a pi zero particle. So, and this is table 43 too. So I'm going to quick grab the textbook and then we'll do this problem. So the table, if you want to follow along, is on page 1179, and it's sort of an abbreviated version of Appendix F, only not for the elements or not for atomic nuclei, but for things even more fundamental than the atomic nuclei. So what we have here is, we'll clear this, and so we have a lambda zero particle decaying to a neutron plus a pi zero particle. And so the lambda zero particle, and we're asked how much energy is released. So Q is equal to the rest energy of the lambda zero particle. So that's 1115.7 mega electron volts minus the rest energy of the neutron, which is 939.6 mega electron volts, and then minus the pion, or the neutral pion, so 135.0. And so you do those together. And you get 41.1 mega electron volts. And so that's the energy that gets released. And so it's not all that different from a nuclear reaction. That's, sometimes you need an input of energy to make an interaction take place, and then sometimes you get a release of energy. So let's do another example. How much energy is released in the decay pi plus, so a positive pi meson or pion becomes a positive muon plus a muon neutrino. So let's again set this up. So that's an anti-muon. And then the muon neutrino that goes with it. And so the energy that's released, you start with the positive pion, that's 139.6. You're subtracting from that the muon, and again, that's the antiparticle. So that's 105.7. But it has the same rest energy as the negatively charged muon. And then the muon neutrino, which has a rest energy at most of 0.1 mega electron volts. So it's 33.8 mega electron volts released in that collision. Okay, so that's the second example. And now we're going to do a third one for good measure. How much energy is required to produce a neutron-antineutron pair? So they both have, this is fairly straightforward. They both have a rest energy of 939.6 mega electron volts. You simply double that. So you get 1,879.2 mega electron volts. So you need that much energy to begin with in order to create a neutron-antineutron pair. So the creation and destruction work both ways. So you can have a neutron and an antineutron annihilating each other and producing that much energy, but you can also have that much energy creating a neutron-antineutron pair. Now we move on to particle stability. So the lifetime of an unstable particle depends on which force is most active in causing the decay. So for the weak force, the decay time is relatively long, by subatomic standards, 10 to the negative 13 seconds. For the electromagnetic force, 10 to the negative 16 to 10 to the negative 19 seconds. For the strong interaction, 10 to the negative 23 seconds. Now, sometimes the particle exists for such a short period of time that you can only infer its existence from the decay products. You can't actually, we don't actually have the means of observing it. We can't resolve the time to a level of precision to observe it directly. These types of particles are called resonances. The resonance has a width corresponding to the uncertainty in its energy. And so the width meaning delta T. So remember from Heisenberg's uncertainty principle, delta E, delta T is equal to H bar, or is equal to or greater than H bar. So there is a limit, there is a physical limit to how the time that's observable, and if the lifetime is, the particle's lifetime is less than that delta T, then we're not going to observe it. So the mean life of a sigma zero particle is 7 times 10 to the negative 20 seconds. What is the uncertainty in its rest energy? So again, from Heisenberg's uncertainty principle, just like delta X, delta P is equal to or greater than H bar, delta E, delta T is also equal to or greater than H bar. And so we want to find the uncertainty in its rest energy if we know the lifetime. So E becomes H bar over delta T. And so H bar is 6.626 Planck's constant times 10 to the negative 34 joules seconds divided by 2 pi, and then divided by the lifetime of the particle. And so that's 7 times 10 to the negative 20 seconds. And then we want to convert this to electron volts. So we have 1 point, is it electron volts or it's mega electron volts? So that's 1.60 times 10 to the negative 13 joules per mega electron volt. So we're including that conversion in here because we're told to express the answer in mega electron volts. And what you get is, I'll put it down here, 9 times 10 to the negative 3 mega electron volts, or 9 kilo electron volts. And so that's the uncertainty in the object's energy. that, with that lifetime, we won't be able to measure um, the particle's energy with any greater precision than that. So this brings us to a new quantum number called strangeness. So we have the kappa, lambda, and sigma particles, and that they're always produced in pairs. Meaning if an interaction produces one of these particles, it produces two. So we have the kaon, the lambda particle, and the sigma particle. And if a reaction or if a collision produces one of them, it produces another. And so that led to a new quantum number called strangeness that is conserved in strong interactions, but not necessarily in weak ones. So the kaons have a positive strangeness, so +1. The lambda and sigma particles have a negative strangeness, a -1. And the chi particles have a -2 strangeness, and the omega particle a -3 strangeness. But again, in strong interactions, strangeness is conserved. And that brings us finally to quarks. Uh, they were first postulated in 1963 and then observed in the 70s. So hadrons consist of three fundamental entities called quarks. So the hadrons are consists of quarks, and so the baryons consist of three, and the other types of hadrons consist of a quark and an antiquark. So the baryons and the mesons. There are 6 types of quarks: up, down, strange, charmed, bottom, and top. So strangeness is conserved, charm is conserved, bottomness and topness are conserved in all strong interactions, but not necessarily in weak ones. And mesons consist of a quark-antiquark pair. So again, the difference between baryons and mesons. Baryons, 3 quarks, mesons, a quark and an antiquark. So you have the different properties. So you have up and down, which don't have any strangeness, charm, bottomness, or topness associated with them. The up quark has a charge of 2/3 E, and again, E is 1.602 times 10 to the -19 coulombs. The down quark has a charge of -1/3 E. So you can think of a proton as being 2 ups and 1 down, and that conserves baryon number and charge. The strange quark has a -1 strangeness. The charmed quark has a +1 charm. The bottom quark has a -1 bottomness, and the top quark has a +1 topness. Now, they each have antiquarks which have the opposite sign. So the anti-strange quark would have a strangeness of +1, and the anti-bottom quark would have a bottomness of +1. So here are the quark compositions for several particles. So for a proton, 2 ups and a down. For a neutron, 2 downs and an up, giving a charge of 0. For a pi meson, again, a quark and an antiquark. So you have an up and an anti-down. And so the down particle has a negative charge, but the anti-down is a positive charge. So you wind up getting +1 here, for the total charge. For a pi negative, you have an anti-up and a down. And for a kaon, a kappa meson, you have an up and an anti-strange. So those are different types of compositions. And so if you look at some heavy hadrons, so whether with mesons and baryons, so you have the combinations of baryon number and charm number, and these will tell you what types of quarks make it up. So you have to have a combination of quarks, and again, mesons have one quark and one anti-quark. Baryons have three quarks, so no antiparticles in a baryon, at least not in a proton or a neutron. There'd be no antiquarks. In an antiproton and a neutron, antineutron, you would have only antiquarks. So that's the important distinction there. So the B meson, to go to another example, is a, and so this is the B minus, is a BU or bottom anti-up quark combination. And so that's on the table on page 1183. Show that this is consistent for all four quantum numbers. So, okay. So you have B minus and bottom anti-up. So for B minus, we know we have so we'll set it up like this. So we have a bottom quark and an anti-up quark. And so first we look at baryon number. And so the B minus is a baryon number of 0. The bottom quark has a baryon number of 1/3. The up quark has a baryon number of 1/3, but again, it's the antiparticle, so it's negative 1/3. And so that's conserved. Now we move on to strangeness. The B minus particle has no strangeness. The bottom quark has no strangeness, and the up quark, whether it's regular matter or antimatter, has no strangeness, so that's conserved. Then we go to charm. The B minus has 0 charm. Read into that whatever you want. And again, the bottom and up quarks also have none. Then we go to bottomness. Now you would expect the bottomness, the bottom particle to have one. So the B minus has a bottomness of -1. And the bottom quark, as you might also expect, has a bottomness of -1. So the matter version has a bottomness of -1, and the up quark has no bottomness. So you see how the properties are conserved like that. And so you can say, well, all right, so this is a reasonable combination, that bottom plus anti-up together make the B minus meson. And so as all these particles started to be found, this led to a development of a theory about particle physics called the Standard Model. And it's basically held firm for over half a century at this point as it's been developed, that the basic theory hasn't had any major shakeups. And so here are the basics of the Standard Model. Each type of quark has its own flavor, but comes in 3 colors: red, green, or blue. So baryons have one quark of each color. And mesons consist of a quark of one color and an antiquark of the quark's anticolor. The fermions obey the exclusion principle and have half-integer spin. And the bosons do not obey the exclusion principle and have integer spin. So now we're introducing another way of categorizing the different particles. So the carriers of the forces are all bosons. The photons, the gluons, the W and Z particles are all bosons. The color force is the strong force between quarks. And the theory of color and the color force is called quantum chromodynamics. So the color doesn't mean anything in a visual way or something on the electromagnetic spectrum. It's just a term, that's used to describe three possible different properties, that the quark could have. Confinement means the quarks are always found in groups that combined have no color. Meaning that if you have red, green, and blue together combined, that's no color. If you have red and anti-red combined, that's no color. If you have blue and anti-blue combined, that's no color. And so the standard model was combined with the weak and electromagnetic interactions through something called gauge theory. And again, so that's where the standard model comes in. And so you have quantum chromodynamics talking about the strong nuclear force, gauge theory talking about the weak and electromagnetic forces. The standard model combines both. And the WZ particles have a mass. They're slowed down in the presence of what's called a Higgs field. So there's a type of boson that regulates that. And that was called the Higgs boson. And so it was theorized in 1964. It took nearly 60 years from when it was first postulated by a scientist named Higgs for it to actually be discovered. So again, theory leads experiment a lot in particle physics. And it has a rest energy of 125.18 giga electron volts, not mega electron volts, giga electron volts. So a giga, so basically that's 125,000 mega electron volts. And so, that gives you some idea of, the size of the particle, and also some idea of its importance, that this was considered the big boson, the one that was elusive, but that everybody expected would be there if you were able to get collisions with enough energy. And eventually they did. CERN got enough energy in its collisions, and they were able to detect the Higgs boson. So Richard Feynman had a way of visualizing the subatomic interactions that involved diagrams. And so you would start with whatever particles were involved. You would include whatever particle affected the interaction, and then you would get the byproduct. So we'll start with beta decay. So a neutron decaying into a proton. So a neutron consists of an up and two downs, and the proton consists of two ups and one down. So somehow the one of the down quarks becomes an up quark, and in the process emits something with a negative charge. So this is considered a weak interaction. So you have the W negative charge, or W negative particle gets emitted from the down quark, and that W negative particle becomes an electron and an electron neutrino. So that's what beta decay is. So the basic process, you have the before particle, you have the after particle, you have the particle with the dashed line that sort of regulates the decay, and then you have the additional byproduct. So the neutron becomes the proton, but there are other particles in it as well. So the process of the neutron emitting a proton, electron, and a electron neutrino is not a one-step thing, that you have the regulator involved in the weak interaction. And so that's the W negative that in this case then decays into the electron and the electron neutrino. Which brings us to, so we can, the standard model unites three of the four forces. The strong from quantum chromodynamics and the electric and weak forces from gauge theory. But ultimately, we want to unite these with gravity as well. And there are some other questions that need answering also. So why do protons and electrons have exactly the same magnitude charge? So there does not appear to be even a small difference between the charge of a proton and the charge of an electron. Why does matter dominate? So we have matter and antimatter, and at the, in collisions, there doesn't seem to be an obvious preference for one over the other, and yet in the universe, matter overwhelmingly dominates antimatter. And that, if antimatter is created, it disappears just as quickly. And so the standard model is considered to be a low energy approximation to a more complete theory, which basically says we need more energy to answer these questions. So we need bigger and bigger accelerators so we can get our answers. So it's speculated that the unification scale is on the order of 10 to the negative 31 meters and involves particle energies on the order of 10 to the 16 giga electron volts. And so we'll talk more about this next week when we get into cosmology, but at this scale, so we're talking the immediate aftermath of the Big Bang, there's no distinction between leptons and quarks or the different forces at this scale. Some unification theories allow for proton decay, but a proton has never been observed to decay. And based on what we do know, the minimum possible mean life of a proton is 10 to the 33 years. So there's a huge limit. Even if protons do decay, there's a huge limit to the lifetime of the proton. So, theories of everything try to unify all the forces, but again, you have to go to energy levels, at least over a small space, that the universe hasn't experienced, at least not that we're aware of, since the moment of the Big Bang. So it's a bit of a challenge. A few logistical hurdles need to be overcome. One type of theory that has some traction, but we're not at the level where we can experimentally verify it, are string theories. So fundamental particles are more like strings with standing waves than like point objects. The problem is we don't have the means of verifying whether the string theory works. So there's a lot of research and thought that has gone into developing string theory. We have no means of verifying that if it works or not. But again, the history of particle physics is the history of theory leading experiment by many decades. So I wouldn't assume string theory can't explain the universe, but we're at a point where I mean, again, where our theories go beyond our technological ability to get the answers, but that's been true for a while, and eventually we do get answers. And it took 60 years to prove that the Higgs boson existed, but it does in fact exist, and it has been observed. Supersymmetry is when each fermion has a corresponding boson with at least the same mass. So, that's another type of theory. So again, going back a couple of slides, the fermion is obeys the exclusion principle. So it's saying that each fermion has a boson, that you should be, that corresponds, that has the exact same mass, or at least is what's postulated in this theory. But it's beyond the ability of today's accelerators to verify this. So again, that's where we are, and so we have theories that we can't test. But as you can see, most of what we have discovered up to this point, as far as particle physics goes, comes from theories that had existed for a while. The theory has pretty much always led experiment, and that's not going to change anytime soon. And with that, we are done with this lecture. So Friday, we will go over some problems, and we'll do another computer assignment. So I will see you then.